12.1, we'll get right away in chapter 12. We're going to talk a little bit about this idea of sequences and series. In the next two lessons, we're going to talk about different types of sequence and series, but 12.1, 12.2, and 12.3 really fit together nicely. But we have to kind of have some background information about what a sequence and what a series are. So, right out of the chute here, a sequence is a function whose domain is a set of consecutive integers. All right? So that just basically says the inputs for the function are consecutive numbers like 1, 2, 3, 4, etc. All right? Now, the terms in a sequence are the values in a range. Okay? We're going to get into this just a little bit more down below, so don't feel completely hung out to dry. But basically, the terms are the range or the outputs of a sequence. All right? A series, okay? A series is best defined as an expression that results when the terms of a sequence are added together. So if I had a sequence of numbers, 1, 2, 3, 4, 5, a series of an expression would be the result of adding these terms of a sequence together. All right? Now, when I add a bunch of stuff together, I use something referred to as summation notation. Summation basically says we're going to take the summation of a bunch of terms, or sum says we're going to be adding them all up. All right? We use this Greek letter sigma. Okay? And I'm terrible at drawing sigma. Okay? There's my sigma. Okay? You guys can pick on me later. That is the Greek letter that we use to represent the summation of a series of terms from a sequence. All right? So, some key things you've got to make sure you understand. First of all, the sequence is the numbers. The 2, 4, 6, 8, etc., etc. All right? A series comes from adding up the terms of a sequence. All right? A series is a sum. A sequence is the actual numbers. Okay? Again, the inputs are the x's, they're consecutive numbers, and the outputs are called terms. All right? So let's fly down below and let's see if we can't take a look at filling in maybe some of the gaps and some of the things we're not quite understanding. Okay? All right. A sequence is a function whose domain is a set of consecutive integers. Okay? Now, what does it mean to be consecutive? It means one right after another. Numbers like 1, 2, 3, 4, and 5, those would be the inputs of our function. All right? If a domain is not specified, it's understood that the domain starts with 1. The values in the range are called the outputs. I'm sorry, that is not correct. They're called the terms of the sequence. The values in the range, again, also called the outputs. When we're talking about a sequence, we call those the terms. All right? So the domain would be the inputs 1, 2, 3, 4, etc., up to n. And then so the outputs, the terms of the sequence, we would call that like a sub 1, which would be the first term in the sequence. A sub 2 is the second term in the sequence. A sub 3 is the third term in the sequence, and so on and so forth. Okay? Now, a finite sequence is one that has a limited number of terms. For example, the sequence down below, 2, 4, 6, 8. We stop at 8. We don't say ... right? So because of that, this sequence stops. And so that would be an example of a finite sequence. Okay? An infinite sequence, and it's weird that we say it one way, we say finite, but an infinite, I can't spell today. All right, let's try this one more time. Okay, infinite. There we go. An infinite sequence continues without stopping. So the second example is infinite because it continues on and on forever. We have the ... at the end, the ellipsis, we call that an ellipsis. And so because of the ellipsis on the end, we mean that we're going to continue that forever. Okay? A sequence can be specified by an equation or also referred to as a sequence rule. Okay? For example, both of the sequence above can be described by the rule a sub n, or the nth term in the sequence, can be found by multiplying 2 by the input of n. Okay, does that make sense? Well, for the first term in the sequence, we take 2 times 1, which is 2. For the second term in the sequence, we take 2 times the input of 2, because this is my input, of 2, which is 4. For the third term, for a sub 3, we take 2 times the 3, because that's the third term in the sequence. 2 times 3 is 6, and so on and so forth. All right? So that would be the rule that represents that finite sequence, or potentially the infinite sequence as well. All right? So let's go ahead and write some terms of a sequence. We have this sequence defined by a sub n is equal to 2 to the n plus 1. All right? So the first term in the sequence then becomes 2 to the n, which is 1 plus 1. This n right here is the term number, and so it's the first term, so 1 plus 1 becomes 2. This becomes 2 to the second power, which is 4. The second term becomes 2 to the 2 plus 1, because again, this 2 goes here. 2 plus 1 is 3. 2 to the third power becomes 8. The next is 2 to the 3 plus 1. That's 2 to the fourth, and 2 to the fourth is 16. The next becomes 2 to the 4 plus 1, which is 2 to the fifth. Again, add these together first. This becomes 32. 2 to the 5 plus 1 is 2 to the 6th, which is the same thing as 64. And finally, 2 to the 6 plus 1 becomes 2 to the 7th, and 2 to the 7th is 128. So that's the first 6 terms of that sequence. A sub n is equal to 2n plus 1. All right? So what happens if we want to write a rule for a sequence? Okay, the first piece then, in lesson 12.1, we talk about writing the rule, and then the next couple lessons we kind of back off that a little bit. We talk about other types of patterning called an arithmetic and a geometric sequence. But for right now, can you see a pattern in this number, in this set of numbers? The number 1, the number 4, the number 9, the number 16, those numbers look like the set of perfect squares. We can write the terms as 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth. So the next term, a sub 5, would be 5 squared, or 25. So a rule for this particular sequence ends up being a sub n is equal to n to the second power. Again, if I want the third term, I take 3 to the second, which is 9. Right? How about the next one? Well, the next one's a little harder to see. 0, 7, 26, 63. Those numbers don't look like they jive so well. But 7 is 1 short of 8. Okay? And 8 is the same thing as 2 cubed. 26 is 1 short of 27, which is 3 cubed. 64 is, or 63 rather, is 1 short of 64, which happens to be 4 cubed. Well, let's go over here. 1 cubed is 1, and I'm 1 short of that. So it looks like if I go 1 cubed minus 1, 2 cubed minus 1, 3 cubed minus 1, and 4 cubed minus 1. Again, 4 to the third is 64 minus 1, which is 63. So it says we can write the terms as 1 to the third minus 1, 2 to the third minus 1, 3 to the third minus 1, and 4 to the third minus 1. So the next term would be 5 to the third minus 1. Oops, minus 1. 5 to the third is 125, take away 1, which becomes 124. So the rule then becomes a sub n is equal to n to the third power, take away 1. All right? Why don't you guys go ahead and try the next 2 checkpoint problems on your own. All right, there are 2 ways to do this. I'm just going to make a chart real quick. I'm going to say for n and a sub n. All right? So for the first term, second term, third term, fourth term, fifth term, and sixth term. We want the first 6 terms of the sequence. Now there's 2 ways to do this. You guys can plug y sub 1 is equal to 3n minus 7, and then use your table feature. Sorry, you can't use n. You're going to have to use an x here. 3x minus 7, and then use your table feature, and then just kind of go take a look at that. Otherwise, we can simply plug in a 1 here. This becomes 3 times 1, which is 3, and 3 minus 7 is negative 4. All right? And then the next one is going to be 3 times 2, which is 6 minus 1, which is negative 1. 3 times 3 is 9, minus 7 is 2. All right? And then so the rest of the numbers end up being 5, and 8, and 11. It looks like that maybe if we took negative 3 to the first power, I get negative 3. Negative 3 to the second power, well, now I get 9. Negative 3 to the third power, I get negative 27, because 3 negatives. And negative 3 to the fourth power becomes 81. So it looks like the next term would be negative 3 to the fifth power, and negative 3 to the fifth power is negative 243. So it looks like my rule is a sub n is equal to negative 3 raised to the n power. All right? Okay, so hopefully those 2 went well for you. Now let's take a look at series and summation notation. So again, a series is a sum of a sequence. It's a lot of S's. We just went ahead and talked about some sequences. A series now says add up all of the terms of that sequence. When the terms of a sequence are added together, the resulting expression is called a series. A series can be finite or infinite. A finite series would be adding in the numbers 2, 4, 6, 8, etc., etc. All right? But we're stopping here at 8. That's a finite series. An infinite series, now that does have the ... on the end, which says 2, 4, 6, 8, 10, 12, etc., etc. Okay, that one I should have said the etc. Okay, so we're in good shape here. We can use summation notation, okay? And we call this also sigma notation, okay, because we're using sigma to say we're taking the sum of these numbers, okay? All right, so if I wanted to take the summation of I equals 1 up to 4 of 2i, or I can take the summation of I equals 1 up to infinity of 2i. And so this is the way we would represent each of those series. For both series, the index of the summation is I. Now, this is not I is equal to the square root of -1. That's an old idea. We're going to leave that alone for right now. We're using I for index. And I just basically replaces the term number. All right? The lower limit of the summation is the number 1, because in both cases we're starting at 1. All right? The upper limit summation, the upper limit of summation is 4 for the finite series, because we're stopping at 4. And it's infinity for the infinite series, because we stop at infinity, which means we never ever stop. We just keep adding those numbers until infinity. So summation notation, as I just said before, summation notation is also called sigma notation, because it uses the uppercase Greek letter sigma written like this kind of goofy looking letter E. All right? Okay, so let's actually do a summation here. It says write series using summation notation. So the first sequence of 4, 7, 10, etc., all the way up to 46. Now we're going to add those terms together, and once I have the plus signs in here, now it becomes a series. All right? Now, in the first one, we have 3 times 1 plus 1 for the first term, because it's 4. It's the number 3 times 1 and then 1 more. And then we go up by 3, and we go up by 3, and we go up by 3. So it looks like it's 3 times 1 plus 1, 3 times 2 plus 1, 3 times 3 plus 1, and the last one is 3 times 15 plus 1. Okay, because there's kind of a so on and so forth in between, because I don't really need to list all of those, but I'm stopping at 3 times 15, because that's 45, and 45 plus 1 more becomes 46. All right? All right, so a sub I then becomes 3 times the index plus 1. All right, so each one of these, we got the first term by doing 3 times 1 plus 1. The second term, 3 times 2 plus 1. The third term, 3 times 3 plus 1. The 15th term, 3 times 15 plus 1. And so for the I term, or the index term I, 3 times I plus 1, where I is equal to 1, 2, 3, all the way up to the number 15. Now, the lower limit of the summation starts at the number 1, because our first value here is I equals 1, and that gives me my 4. The upper limit is the number 15, because I'm stopping at 15. All right? Because again, 3 times 15 plus 1 gives me the 46, which is the last term in that sequence. All right? So the summation notation would be the summation from I is equal to 1 up to 15 of the expression 3i plus 1. All right? We're adding up all the terms, 3i plus 1, from 1 up to 15. All right? And that's summation notation. In the second example, this dot, dot, dot says we continue forever. All right? So if you take a look, each of the denominators is a perfect cube. This is 1 over 1. This is 1 over 8. This is 1 over 27. Well, this happens to be 2 cubed. This is 3 cubed. And yeah, that's 1 cubed. 4 cubed happens to be 64. And you'll notice the next one is 1 over 64, and so on and so forth. All right? So each one of these looks like it's 1 over the index, whatever the index is, cubed. Okay, 1 over the index cubed, or 1 over I cubed. All right? Where the index now is 1, 2, 3, 4, etc., all the way up to infinity. The lower limit of the summation becomes 1, right? Because 1 over 1 to the third is just 1. And the upper limit is infinity. All right? So we're going to take the summation from I equals 1 up to infinity of 1 over I to the third power. Okay? And that's my summation notation for example number 3. 2 checkpoint problems for you guys to try at the top of the next page. Let's see how you do. Go ahead and see if you can't write with summation notation. All right, in example 3, this is just 7 times 1, 7 times 2, 7 times 3, and this is 7 times 11. So basically I want 1, 2, 3, 4, 5, all the way up to 11. And so I want the summation of I equals 1 up to 11. And basically it's just the number 7 times whatever the index is. So 7 times 1, 7 times 2, 7 times 3, etc., all the way up to 7 times 11, which is my 77. So it's the summation from I equals 1 up to 11 of 7i. All right? Now the next one, it's negative 4. And if I change this to plus negative 8, plus negative 12, plus negative 16, etc., this becomes negative 4 times, negative 4 times 1, negative 4 times 2, negative 4 times 3, negative 4 times 4. So it looks like this is my index, and I'm just taking my index and multiplying it by negative 4. So it's the summation of negative 4i, starting at I equals 1 and going up to infinity. Again, this is an infinite series. This is a finite series because it stops at 77. All right? What happens if I ask you to find the sum of a series? Okay. Well, I want to know, now we're just using k instead of I. It doesn't really matter. We just typically use I for index, so I'm not sure why we switched to k here. We're starting from k to 3 up to 5. So that says my sequence is 2 minus 3k, where k is equal to the number 3 up to 5. So 3, 4, and 5. You'll notice each one of these says 2 minus 3 times k, 2 minus 3 times k, 2 minus 3 times k, where k is 3, 4, and 5, because those are the numbers from 3 to 5. Now all we have to do is simplify each one of these expressions. This is negative 3 times 3, which is negative 9. 2 minus 9 becomes negative 7. Okay, the next term is negative 12 plus 2, which is negative 10. And the last term becomes negative 15 plus 2, which is negative 13. And so altogether we end up with negative 30 here. All right, now, a couple of special series. Special series. These are just ones that we use in special occasions, okay? Not all series look like this, but these are some rules that you're going to want to familiarize yourself with. First of all, the sum of n integers up to 1, okay? n terms of 1. So that says I want to take the summation of I equals 1 up to n of the number 1. Notice that this doesn't have anything to do with the index here. It's just the number 1. So it's the number 1 added up together n times. So what if this was 5? It'd be the number 1 added to itself 5 times. Well, 1 plus 1 plus 1 plus 1 plus 1 becomes 5. So basically, if you look back at that now, okay, whatever this number is, if it's the summation of the number 1, well, it's just going to be that number right there. All right? The first n positive integers. So if I wanted to find the sum of the first integers, the first positive integers from 1 up to, say, 51, for example. Okay, I could do 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., all the way up to 51 in my calculator. Or I can use this shortcut that says the summation of the index I. Okay, we're not doing anything to these numbers, just the number 1, the number 2, the number 3, right? So it's the summation of the numbers that are the indexes from 1 up to n becomes n times n plus 1 divided by 2. Okay, so we multiply the number times n plus 1 and we divide it by 2. Okay? Now, what about the sum of squares of the first positive n integers? Okay, this one seems a little bit trickier, but we're now just talking about the squares. We're talking about all the perfect squares of each of those numbers. Okay? So if this was like 6, for example, we would want 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. And instead of doing all of that, now again, that might not look like it's that hard if you're looking at this formula here, but you can certainly do this up to maybe 16, and now you can see that this would have to go on forever, for a little bit longer anyway. So the shortcut to do that then becomes n times n plus 1 times 2n plus 1, divide the whole thing by 6. Okay, and so that's the summation of the first n perfect squares. All right? So let's take a look at that formula then, and let's see if we can't use that to simplify using a formula for a special series. Okay, my special series now says the summation of 1 to 32 of the number I. Okay, that's this middle pattern right in here. Right, that's that middle pattern. I can't see it on the screen, but you guys can certainly see it in your book. Okay, it's basically the sum of the first 32 numbers. Okay, so this becomes 32 times 32 plus 1, divide the whole thing by 2. All right, 32 times 33 divided by 2 ends up being 528. So if I added up all the numbers from 1 to 32, I would get 528. Now if I multiplied the numbers from 1 up to 32, that would be something called 32 factorial. That's chapter 10. We're not doing that. Okay? So we're just going to use these shortcut series. Okay? All right, how about example 5 and example 6? You try those, pause your video, and give those a shot. We'll be right back with a solution. All right, this one's a little tricky, but we've got to have 4 squared minus 6 plus 5 squared minus 6 plus 6 squared minus 6 plus 7 squared minus 6 plus 8 squared minus 6. And if you want me to, I can put brackets around each one of these or parentheses or whatever you like. Okay, so here's when my index is 4, 5, 6, 7, and 8. So I'm going from 4 up to 8, so I need all of those terms. And then I just have to simplify. 4 squared becomes 16, 16 minus 6 is 10, 5 squared is 25, minus 6 is 19, and so on and so forth. I'll let you guys do the math on that one. But you end up getting something like 160 here. All right, if you got 160, you're in good shape. If you didn't, you might just want to go back and check your math in here. All right, now I want the summation of the first 28 perfect squares. That's 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared, all the way up to 28 squared. That's going to take me a while. So instead of doing it that way, I'm going to use 28 times 28 plus 1. And that's the rule that's up in here, guys. It's right above that mark here on your page. And then this becomes 2 times 28 plus 1. Because again, the last is 2n plus 1. So it's n times n plus 1 times 2n plus 1. And we're going to divide the whole thing by 6. All right, now, I don't really care what this number is. I'm simply going to do 28 times 29. 2 times 28 is 56. 56 plus 1 is 57. So I'm going to do 28 times 29 times 57, divide the whole thing by 6, and I get 7,714. Oops, that's terrible. 7,714. All right, and so that would be the sum of the first 28 perfect squares. All right, and that concludes our lesson on 12.1.